as a media file and then upload it to the classroom, which is a little more work, but let's work with it anyways. Alright, you guys still hearing me?
Yes, sir, that would be much appreciated.
Alright, so this is the rate at which work is done, or energy is converted. Right? So the rate at which work is done, or the rate at which energy is converted. So that is power, right? Rate at which work is done, or the rate at which energy is converted. Now, what we need to be aware of, remember we said that potential difference, right? It's the work done, right? When 1 coulomb of charge is moved from one point to another in the circuit, right? Now what we need to be aware of is whenever that charge moves, right, or whenever work is done to move that charge, energy will be converted. Okay?
Yes, sir.
So whenever work is done, what we need to be aware of, generally speaking, whenever work is done, energy is always converted, right? Whenever work is done, energy is always converted. Are you with me?
Yes, sir.
Right? And that is why, you know, when you get up in the morning and you start to do some jogging, you know, or you do some push-ups or whatever, right, you start to sweat. Because when you do work to actually move your body, right, when you do work to move your body, as I said, energy will be converted, right? So the energy, or the chemical energy, will be converted to other forms of energy. In that example, right? So whenever work is done, energy is always converted. So power now is the rate at which work is done, or the rate at which energy is converted. So when that charge moves, because again, potential difference, it's the work done when 1 coulomb of charge moves from one point in a circuit to another point. Now when that coulomb of charge moves, as I said, and work is done in moving it, energy will be converted, right? Now in that case now, we can look at, okay, how much energy is converted over a period of time. So we know that power is the rate at which work is done, or the rate at which energy is converted. So we can write that power P is equal to what? In terms of energy, power P will be equal to what?
So energy over time?
Absolutely, has to be energy over time. Kiara?
Yes, sir.
Yes, good evening. Can you hear me loud and clear?
Yes, sir.
Okay. So power is energy over time, just like this, right? Power is energy over time. Now we can remember that when we were talking about PD, we said that PdV is equal to the charge, sorry, not the charge, energy over charge, right?
Yes, sir.
Energy over charge. Now taking this equation right here, could we rearrange this to make energy the subject?
Which one, sir? The
V equal E over Q.
yes, sir.
What would we get when we make E the subject?
So we'd get V multiplied by Q equal E.
Right, so energy E is equal to the charge multiplied by the potential difference. So the energy E is equal to Q times V. So now, taking this information right here, we can substitute this for E in this formula, true?
Yes, sir.
Alright, so let's do that and see now. So we're going to say now that P then now is equal to the energy, which is the charge Q multiplied by the potential difference V, and that is being divided by the time T. Yes?
Yes, sir.
Now, somewhere before, we would have written an expression for Q in terms of current and time. So charge Q in terms of current and time is equal to what?
So now equal to current multiplied by the time.
Absolutely, right? So it's a Q is equal to I times T. So now, it turns out then now that since we know that Q is equal to I times T, we can actually rewrite Q in terms of I and T. So we can say now that P then now will be equal to Q, but Q is equal to I times T. So we're going to say I times T multiplied by V, which is the potential difference, and that now will be divided by the time. Follow?
Yes, sir.
So now, as a result of that now, we can see now that we can simplify this because we have t in the numerator and t in the denominator. So we'll cancel like that, and we're going to see now that we can calculate electrical power by saying that power P is equal to the current flowing I multiplied by the potential difference V. Okay?
Yes, sir.
And this is our first formula for calculating electrical power. Okay? So this is our equation 1. Yes?
Yes, sir.
Kiara, do you follow this?
Yes, sir.
Alright? So we get P is equal to I times V. Right, this is the first equation we need to be aware of. Alright? Now, for the most part, you're not going to be required to prove this. Alright? But, I mean, it's good to be aware of, how it actually makes sense in terms of deriving this formula. Right? So, that's what we get. Now, we know of this very fundamental formula, or very fundamental law when it comes down to electricity. And I'm not sure if I would have mentioned to you that, once you're studying electricity, the most important law you will have to know is Ohm's law, right? Because everything else can be explained based off of Ohm's law, right? Every other law you're going to come across can be tied directly back to Ohm's law. So Ohm's law is one of the most important law in terms of electricity that we need to be aware of. So we would have talked about Ohm's law before, and we said that with Ohm's law, whenever we have a conductor, right, at a constant temperature, right, the current flowing through it will always be directly proportional to what?
Ends.
Not the ends.
Potential difference.
Yes, the potential difference across the ends, right? So the current flowing through it will always be directly proportional to the potential difference across its ends, right? And as a result of that, we get that V, which is the potential difference, is equal to I times R. Okay?
Sir.
So we can say now that from Ohm's law, we know that V is equal to I times R. So now, because we have P is equal to I times V, we can actually substitute this into this formula right here. So let's see now. So V is equal to I times R. Right, let us say this is equation A. Right, I don't really need to, but let's say equation A. Right, equation A. So this is equation A. So now, P is equal to IV from equation 1, but V is equal to IR from equation A. So what we're going to do now is we're going to substitute this into this. So we're going to say P is equal to I times V, right? But again, V is equal to I times R, right?
Oh, yes, sir.
So now we're going to get that P is equal to I times V, but V is equal to IR. So we're going to have I multiplied by I times R, because I times R is V. So now we can take it a step further, and then we just multiply. So when we multiply I times IR, we're going to get what?
IR.
I times IR would give you what?
Oh, IR squared. So I squared R.
Right, I squared R. Not IR squared, but I squared R, because we're going to get I times I, which gives us I squared, and R will just remain. So we get I squared R. Okay? So this right here now is your second equation for calculating electric power. Okay? So equation 3. Yes? Question?
Sir.
Now again, taking Ohm's law, we know that V is equal to IR, but we could make I the subject. Right? We could make I the subject. When we make I the subject, we're going to get I is equal to V over R. And again, we know that P is equal to IV from equation 1, right? But I is simply V over R. So what we say now is P will be equal to I which is V over R, so we get V over R multiplied by V. So what do we get in this case now? We're going to get P is equal to what?
V squared R.
V squared over R.
Over R, sorry.
Right? And this is the third equation for calculating electric power. So any one of these we can use to calculate electric power. So this was supposed to be 2 right here, sorry. And this is 3. So this is our third equation. So now, if you're given the current and the potential difference, you can use this to calculate the power. If you're given the current and the resistance, you can use this one to calculate power. If you're given the potential difference and the resistance, you can use this one to calculate power. Okay? Chrisan, make sense? Make sense, Chrisan?
Yes, sir.
Right? So these are the 3 equations for calculating power. Any question, Kiara?
No, sir.
Okay. Alright, so let's see if we can look at an example. So let's say a resistor, let's say a resistor is connected to a 12 volts battery. It's connected to a 12 volts battery and a current of 1.4 amperes flows through the resistor, right? Through the resistor. The resistor. Let's make it an A-B question. So question A, calculate the resistance of the resistor and so calculate the resistance of the resistor, and B now calculate the power dissipated. I guess we're going to work this as an example. Dissipated in the resistor. So now, first thing we need to do is to calculate the resistance. So we're going to say Ohm's law, V is equal to IR. So now, since we're trying to find R, we rearrange. We're going to get R is equal to V over I, right?
Yes, sir.
So now we just substitute. So V is the potential difference, or in this case the EMF. And I'm going to define for you the EMF, right? So 12 volts.
So not about that.
Yes, it's a voltage. But you see, the thing is, the technical definition for EMF and potential difference slightly differ, right? But,
okay.
But generally speaking, they're both voltages, right? Because when we talk about EMF, we talk about the energy converted, the work done when energy is converted at a battery. So when energy, let us say of one form, is converted to electrical energy at a battery or a generator. So that's the technical definition.
So it's so specific.
Exactly. Exactly. That's why I said it's just the technical definition of both. But generally speaking, they're both voltages, right? They're both voltages. So the EMF of the battery is 12 volts, and technically we normally say EMF of a battery, right? And the PD across, let us say for example, a resistor. Okay? That's just, as I said, the technical way of looking at it. So V now is the voltage of the battery, or the EMF of the battery. That's 12 volts. And we're going to divide that by the current, which is 1.4. And what do we get when we work this out?
8.57.
8.57, so we can say 8.6.
Yes, sir.
Right, so 8.6 ohms, right? So resistance is 8.6 ohms. Now they say we need to calculate the power. So to calculate the power now, we're going to say that P is equal to IV, right? So we can use P is equal to IV, where I is the current flowing through the resistor, and V is going to be the PD across the resistor, right? Now, because the resistor is connected to the 12 volt battery, only the resistor is connected to the 12 volt battery, what we're going to see is that the EMF of the battery will be equal to the PD of the resistor, or the PD across the resistor, okay?
Yes, sir.
So for that now, we're going to say that I, which is the current flowing, is 1.4 amps. So we're going to have 1.4 amperes, and V is the PD across the resistor. Again, since it's just one resistor, the EMF of the battery equals the PD across the resistor. So this is going to be what? V, which is the 12 volts as well. So now, after multiplying
So
these...
8.6.
No man, 8.6 is the resistance. We're going to use the formula with the resistor as well and see if we get the same value shortly.
Oh, resistor.
Right? So what's this now when we multiply these two?
So 16.8.
So 16.8, and the unit for power? Remember. What
The
is,
joules?
no, what is the unit of power?
So joules per second?
Yeah, you could go with joules per second, you know. You could say joules per second. Right? I heard somebody, was it Kiara, where you were giving an answer? Was it Kiara who was going to respond a while ago? Kiara?
So are you hearing this?
Yes, I'm hearing you now.
I'm sorry, so it's what?
Yes, what? So what is the unit of power?
Oh, I'm forgetting us, sir.
Yes, and I even said it. Thought you'd catch on, right? Or you could get away with joules per second, you know, because it's the energy over time. So joules per second. Right? So that's that. And we could also, as I said, we could work it out where we say that P is equal to what alternately? P is equal to IV, or P is equal to what?
So V2, V squared over resistance.
Over resistance, right? So now, V is going to be the same PD across the resistor, or the same as the EMF of the battery, which is 12 volts. So we're going to say 12 volts. So override volt again, V. And we're squaring this divided by the resistance, which is 8.6 now. So we get 8.6 ohm. So how this work out? What we get when we work this out?
So you get about 16.7.
Right, we're going to get 144 divided by 8.6, so 16.74.
16.74. So,
Right? So 16.8. Right? Same
so
16.
now I'm 16.8.
Oh, 16.74? Exactly?
Yeah.
16.74. And I guess because we remember we round this up to 6, so if we had to use the 5/7, so if we say 12 divided by 8.57, we should get the same 16.8. So it's because we rounded right here. So 12 squared, which is 144, divided by 8.57, I think it was the answer I was getting, or somebody had said it. Right, we get the same 16.8. So it's because of the rounding, right? So that's that. Alright?
Sir,
Yes.
sir, question.
Yes.
Sir, is the same thing you do but in two different methods?
Yes, same calculation, but we're using a different formula. Remember, P is equal to IV, P is equal to V squared over R, or we can also have P is equal to what? What's our next formula for power? Electric power.
T squared R.
Not T squared, but I squared.
I squared.
Yes.
Sir, right.
Right? I squared R. So I is the current through the resistor. So the current through the resistor was what?
1.4 ampere.
Right, so 1.4 ampere. And we take the square of that and we multiply it by the resistance, which is the 8.6 ohm. Right? And this works out to be what now?
I get 24, not get 16.
1.4 squared times 8.6.
Yeah, 1.4 squared
8.6.
times 8.6. Oh yeah, I get about the 16, yes sir.
Right, so
no, we get 16.9.
Right, because again, because we round the resistance, right? So that's how we get the different answer, right? So 16.8, and again because we rounded the resistor, because remember it was like 8.5 something, so 8.8. I mean 16.8. Just because of the rounding, so values are all the same. It's just because we did some rounding when we were calculating the resistance. Because remember when we were working out the resistance, we said thing there were V over I to find the resistance, and the V was the 12 divided by the current, which was 1.4. I would have gotten 8.57, but we rounded that to 8.6. So that's why we got slightly different answer, but they're technically the same. Okay? That's good?
Yes, sir.
Alright, that's good. Okay. So now, what we're going to talk about now is we're going to talk about resistance in series and resistance in parallel. Alright, so let me make some space for that. Alright, let me make some space here. Hold on a second. This is a graph paper. So, do we have any questions so far? Everything is clear? Everybody able to follow what's going on and appreciate what we just discussed? Huh? Nobody appreciate it?
Yes, sir. But what do you mean by what is all about the resistance, sir? Different resistance, them?
Alright, let me go back up. Remember when we were calculating the resistance here? Wait a second, screen like it froze. When we were calculating the resistance at some point, for this same question right here, when you divided 12 by 1.4, you got 8.57. But because we rounded this to 8.6, that is why our values are slightly different, especially when we use the formula involving the resistance. Because instead of using 8.6, we should have used 8.57 to get an exact value of so that's why it was varying, right? But as I said, they're almost the same, because if we were to round these to just two significant figures, it would be 17 and 17 all across. Just because of the rounding, why the values are slightly different. Okay?
Yes, sir. No, I understand.
Right. So, Kiara, that's okay?
Yes, sir.
Right. So now we're going to talk about resistance in series and resistance in parallel. But before we do so, let me write the definition for you for EMF. Right? Let me write the definition for you for EMF. Right. So here.